All right. Okay, so my name is Jonathan Ayub, and I chose to present on automated unit testing. We're going to be focusing more on unit testing and memory testing as opposed to integration tests or what have you. But I have been doing or writing automated unit tests for several years. Let's see, probably three or 4 years. I actually was working on a project and they wanted to look into unit testing because we were starting to implement an MVC framework, and we knew that unit testing was something we would be able to do with that. And so I started researching unit testing, and that actually led me to the topic of dependency injection. And so it all kind of went from there. Ever since then, I've been doing unit testing and using dependency injection and other techniques pretty extensively. And also doing some test-driven development. So I've found it to be really useful, and it's definitely a big part of my development process nowadays, and so I thought that I would share about this. So, a summary of what we're going to go through. First, we'll talk about some prerequisite skills that you might need before you try writing automated unit tests. Then we will define what automated unit testing is and why you might want to do it. We'll talk about qualities of maintainable unit tests, how to write handwritten fakes, how to use testing frameworks, test naming and organization. Then we'll talk about the difference between unit versus integration testing, and then we will talk about TDD a little bit. So some prerequisites. Before you start writing unit tests, there are some skills that would be valuable to you, and first of all is object-oriented programming. Obviously that's a foundational skill that you would want to have one way or the other, but when you follow object-oriented programming concepts and techniques, it makes your code a lot easier to test. If you are not writing object-oriented code, then it's going to be very difficult to test your code because it is not loosely coupled, and usually with procedural code, there's a lot of logic all in the same place, and it's hard to separate that logic and test it independently. Another skill that you would want to be familiar with is SOLID. That's an acronym. I'm not sure if all of you guys have heard of it, but it's basically solid object-oriented principles. There are some principles that kind of define what object-oriented code means. And so if you're following those principles or those ideals, it usually means that your code is more object-oriented. Also, you want to be familiar with writing testable code. Before you can test your code, it has to be testable. So dependency injection is one strategy for making your code testable. So that's another skill that you would want to read up on. So what is automated unit testing? So first we'll define unit testing. This is where you invoke a unit of code or a section of code, and you check the correctness of the results. If the results are incorrect, then the unit test has failed. So what do we mean by unit? Well, a unit is a use case or a unit of work within the system. So it's a series of actions that occur between invoking some code and a single noticeable end result. Whether that end result is a return value, a change of state in the system, or a call to a method on a dependency. So the class or code that you are testing is many times called the system under test, abbreviated SUT or SUT. So you'll hear me refer to the class that you're testing as the SUT many times throughout the presentation. So just be aware that's what I'm talking about when I say SUT. I'm talking about the class you are testing or the code that you are testing. All programmers typically do unit testing of some kind. I'm sure you guys have all heard of unit testing. Usually it is usually done by starting up your application, navigating to an area where you have some code you want to test, and pushing a button that invokes that code, or maybe issuing a command on a command line program, or sending a request to a web service, or different things like that. So the typical thing that programmers will usually do when they're writing code is they'll write the code, then they'll start debugging. They'll start up their project, their application. If you have a website or a UI of some kind, you'll have to navigate through to the section of the website where your code is invoked, and then you'll have to click a button or something like that, and then you'll watch the code that you just wrote start running, and then you'll see if the results are what you expected it to be. This is actually really clunky, and so automated unit testing actually uses code to run unit tests that a human might perform, but it does it in an automated fashion. So good unit tests isolate units of code from their dependencies. So that's what we're talking about tonight, is doing this, doing unit testing, but doing it in an automated way, writing code to test code. So now we're going to talk about why you might want to write automated unit tests. And first I'm going to talk about some objections that people typically have to writing unit tests, and then I'll go into reasons why you might want to consider writing them. So some objections that people sometimes have is that automated unit tests are made out of code, and that means that you have more code that you have to maintain in your code base. So typically when you write production code and then you write unit tests for that production code, it may double or even increase the amount of code more than that, because you have your production code and then you have your automated unit test code. So sometimes people will say, well, you know, why would we want twice as much code to maintain? So that is one objection that people might have. Another one is that there's a perception that writing automated tests makes a project take longer. So you know, if you're writing more code and you're writing automated tests, then that means there's more code that you need to write. And so the kind of theory there is that because there's more code, it's going to take longer to finish the project. Also, there's a learning curve involved. So I mentioned the prerequisites that you might need before you start writing automated unit tests. And not all developers are up to speed on all those prerequisites. And sometimes they can be a pretty tough learning curve for some people. And so that's another objection that people sometimes have, is that, well, in order to write automated unit tests, we have to be familiar with all of these complex concepts. And so they won't take it on because they don't want to have to get over the learning curves. And so one potential solution that I have for that is just to start small. You can write very simple, very small unit tests. You don't have to eat the entire dinosaur at once. You can just start small and write very simple tests. You can write a test that'll test anything, and it's actually great just to get a test project started and get it all configured and get it hooked up to your production code. That in itself is a great step. And then you can write a test as simple as, does this class implement an interface? That's not a very useful test, but when you're starting simple, it's a good way to at least get started, get familiar with setting everything up, and get familiar with the frameworks involved. Developers and other members on the team need to make effort towards learning these concepts, so the prerequisites. if you don't have buy-in from all members of the team on taking on automated unit testing and learning all of the skills involved, then it's going to be difficult to be successful when you're trying to implement it. Another objection is that a team may have tried to write tests in the past, and maybe these tests became unmaintainable. They were very difficult to keep passing. They kept failing, and then the diagnostics was not very good, and so they thought, so it became unmaintainable, and maybe they got burned in the past by taking something like this on. But a solution to that is that you can learn techniques to write maintainable tests, and you can avoid some of the issues that can come up. So to start, talking about some potential solutions to these objections. First of all, I'll talk about the first objection that I listed, which is that when you're writing unit tests, they are code, and it can sometimes make your code base much larger than it would have been before. And kind of a solution to that is that you can write tests in a maintainable way, so it can minimize the maintenance overhead of the test code that you write. Another thing is that when you write good unit tests, it makes your production code more maintainable, because when you make changes to your production code, the automated tests will run, unit tests immediately within seconds, and it will let you know if your production code is still working as expected. So there are a couple graphs I have on the right-hand side here, and it compares project size to the total amount of time that might be spent on that project. So one graph here has a comparison of test-driven development, or code written with TDD, compared to code written with no tests. And if you look at it, as the project size increases, the total maintenance time spent on the project or on developing the project starts becoming less as the project size increases compared to code with no tests. And that's because as your project size gets larger, the complexity gets larger, and it gets pretty much impossible for one person to completely understand the intricacies of everything in the project. And so when you have automated unit tests there, in order to check if your production code is running correctly, all you have to do is run the tests, and they run immediately, and they run the exact same way every time. And so as you start to add more and more functionality to that code base, you can keep running your tests, make sure that the code still runs correctly, rather than potentially, as you keep adding features to the project, running into start creating bugs because you don't have automated tests, and some changes that you make cause issues that kind of slip through the cracks. So that's kind of one idea that proponents of automated unit testing will tell you, is that as your project size increases, the actual amount of time spent on the project will be less if you have automated tests. So now I'm just going to give a very simple example of an automated test, like a Hello World test. So we've got a class here called Hello World class on the left, and it has one method called execute, and all that does is return a string that says Hello World. And then on the right-hand side next to that, we have a test for our Hello World class. And there's one method in that test, and what it does is it instantiates an instance of the Hello World class, then it executes the method on that class, and then it makes sure that the result returned is the string hello world. And if it isn't, then it throws an exception with a message saying that we did not receive our expected result of hello world. And to run this test, basically you could make a small console app and you can instantiate your test class and run the test method that, that runs the test. So that's just a really simple example. That is an automated unit test. It's just basically instantiating your SUT, or system under test, running a method, and then checking the results. All right, so now we're going to talk about some principles of maintainable unit tests. So one of the main concepts involved with automated unit tests is arrange, act, assert, tear down. These are the 4 steps of an automated test. A lot of times it's abbreviated AAA or AAA. And every automated unit test you write should basically have these 4 steps. The reason that the acronym is just AAA is because for the most part in a unit test we don't need to tear down anything because C# has a garbage collector and that takes care of cleaning up for us. But you should be aware that the tear down phase is necessary for some tests. So the arrange phase is where you set up the initial state and conditions of your test. When you're writing a test, you are setting up a condition to test, basically. So that involves setting up some data. You might create some fake test data, and then you'll also create the SUT. You might configure fake dependencies or singletons, etc. So everything that is needed to set up the circumstances or the scenario of your test is what you do in the arrange phase. The act phase is where you actually call the method of the SUT that invokes the code that you're testing. And then the assert phase is where you verify that the expected result was achieved. This is done by checking a return value, checking a publicly observable state change in the system, or verifying that the SUT interacted with a dependency correctly. The teardown phase is where you put all the data that was set up in the arrange phase back into its original state. You free resources, put singletons back into their original state, etc. And like I said, usually in C# we don't have to worry about this phase because the garbage collector is going to do it for us. But you have to keep in mind that in any kind of data that you arrange in the arrange phase, if that data is going to be left around, if it's going to be there as you continue running additional tests, that data needs to be reset back to its original state. The teardown phase is especially important in integration tests because in integration tests you might actually be inserting data into a database or writing files to a file system, and anything that you do like that needs to be teared down, like the data needs to be deleted from the database or those files need to be cleaned up. So test code needs to be maintained just like production code, so that it's essential that your test code follows the same quality standards as your production code. There's a kind of prevailing attitude, I would say, about automated unit tests, that the unit tests are not as important as production code because your clients might not really know that the unit tests exist, but they know that your production code exists because they're using your website, they're using your tools, or what have you. So sometimes the unit tests are a second priority behind the production code, and sometimes it can slip down to where unit tests are just kind of an afterthought, or the quality of the code written for those tests. So developers might not put the same quality standards towards their test code as they do their production code. And when you start doing things like that, that makes your test code less maintainable, and it makes it so that in the future, when you have to modify those tests, or if those tests fail, it's going to be that much harder to figure out what's going wrong or change your tests to adapt to your changing production code. So you need to follow maintainable code principles like dry, don't repeat yourself, don't have duplicated code between your tests, refactor common test code into classes or into methods or what have you. Also follow the single responsibility principle. One of the principles is that every test class should test one unit of work or one scenario in the system. So you shouldn't have a test class that's really huge that tests a whole lot of different unrelated things. At the same time, when you have a test class that's starting to get very large, that might be a sign that your production code your production class is also too large and that you need to break it down into smaller classes. So there's a set of principles called FIRST, and these are maintainable test principles. So I'll just go through these principles. First of all, your unit tests should be fast. They should run in milliseconds. You have to imagine that every time a developer is writing new production code, they are running your tests. And if you have 700 tests in your unit test suite, those tests need to run fast, or the developers are not going to run them, because they're going to know, hey, our unit test suite takes 2 minutes to run. I don't have time to run all of those things before I start writing more code. So they need to be fast so that you can get fast feedback, so that as you adjust your production code, you get fast, quick feedback whether there's a failure. Now, more recently, there have been some frameworks coming out that support continuous unit testing, and what they do is they look at your production code as you're writing unit tests, and they will run unit tests, the specific unit tests for the production code that you're changing continually as you keep writing production code. This can give a little bit more flexibility towards this FAST principle, because your continuous test framework will be continually running the specific tests that need to be run as you are changing your code. So there's a little bit more flexibility there, but again, there's a threshold to where unit tests cannot be, super slow. So isolated, each test needs to be isolated from every other test. So no test should leave any residual state, as I said before. You should always have that cleaned up. Each test needs to arrange the needed state for the test, and it resets or cleans it up if needed. You should get the same test results no matter what order the tests are run. So there should be no dependencies between tests where one test is setting up something that's needed for another test. Also, tests should not expect that other tests have set up certain state. You have to make sure that there should never be a condition in your code where unit test 1 needs to run before unit test 2, which needs to run before unit test 3. It should not matter which order your unit tests run. They should be able to be ran in any order and still pass. There should be one logical assert per test. So every test should test one thing, basically, logically. You should not have a test that tests every single thing in a class. It should be a logical, each test should be a logical unit that is testing one use case in your system. And tests for a class should not fail because of an issue in another class, which means that classes should be isolated from their dependencies. So if you have a test for a class, that test should not fail because a different class that you are not testing has a problem. So the R in first test should be repeatable. A test method should not depend on any data in the environment or instance in which it is running. So a lot of times this is an issue with integration tests where you expect certain data to be in a database or something like that. But you could also expect a singleton to be in a certain state for your unit tests, and that's something you should try to avoid. And results should be deterministic, so they should yield the same results every time and at every location where they run. There should be no dependency on date, time, or random numbers. And we will actually get into an example where we isolate our code from the system time. So the S in first stands for self-validating. There should be no manual inspection required to test, to check whether the test has passed or failed. So the test should tell you if it's passed. And they should be timely. This first acronym is actually kind of a test-driven development acronym. So they will say, test-driven development proponents will say that your test should be written before the coded test. But I'll mention that that's kind of, if you're just starting out with automated unit tests, that's not something you need to worry about right away. I wouldn't try to get into TDD immediately necessarily if that seems intimidating or whatnot. But proponents of test-driven development would say you should write your unit tests first before your production code. So when a unit test fails, it should be easy to detect what was expected and determine how to pinpoint the problem. So a developer 2 months from now should be able to understand why a test failed, if it does, without debugging the test or reading the test code or the production code. Unit testing frameworks make it a lot easier to write unit tests, so you should use them. And they should be organized and modular. So just like you organize your production code in modular ways, and you have a folder structure and naming conventions, you should also have similar principles and conventions for your test code. So now we're going to talk about writing testable code. So I mentioned the SOLID acronym before, and the D in SOLID stands for the dependency inversion principle. This principle's main concern is for writing maintainable production code, but following it will make your code loosely coupled and testable. So basically, if you use dependency injection, that is a strategy that will make your code isolated and testable. So when we say loosely coupled, that means that your classes do not have strict dependencies or specific dependencies. They are not specifically dependent on other classes. And if you've looked at dependency injection before, you'll know that that's achieved through the use of interfaces. Basically, your classes don't have hard references to classes. They use interfaces so that the code is it's aware that it's relying on an interface, but not a specific implementation. So for your code to be testable, you have to isolate it from external dependencies, like I said, but mainly that means you should not be dependent on file systems, threads, memory, time, data stores, and so on. So you shouldn't be directly accessing your database and your classes. You should not be directly accessing a web service. You should be relying on interfaces. Dependency injection is kind of a big topic, but kind of a rule that you can follow is that you should isolate your code from unstable dependencies. These are dependencies that might change over time. Usually they mean your production code or classes that access a database or a file system, outside resources, and things like that. So here's an example of using dependency injection to isolate your code so that you can test it. We have a customer registration class on the left here, and you'll notice in its constructor that it takes two interfaces, a customer repository interface and a date-time interface. And then those are assigned as class level variables. And then there's one method in this customer registration class called register. And basically it retrieves the customer that you are trying to register from the repository. And like I said, you don't have a strict dependency on a database or a file system. You just have a reference to a customer repository. It could be a web service, it could be a database or a file system, it doesn't really matter. But basically this register class retrieves the customer, it sets the registration date of the customer to the current date, and then it updates that customer. So basically that's what the customer registration class does. And then we have our repositories on the right. So the customer repository has two methods, a get method where you give it an ID and it gives you the customer back, and then an update method where it updates the customer. And then we have a date time interface, which basically just returns the current time. So that may look kind of weird. Like, why do you have an interface for date time? Why don't you just use date time? Well, that's so that you can control the time in your tests. You can basically give any implementation of that date time interface and tell it what time to return. So it isolates your classes from the system time. So now we're going to look at isolating code with fake implementations. So when you write loosely coupled code, like the example that I just showed, it lets you substitute any implementation for an external dependency. So this means that you can give your production code test implementations that you have control over. So one of the first principles that we went through is isolation, which means that tests should be only testing the code in the set, in the class you're testing. Like I said before, tests should not fail because of an error in a different class that is not related to your test. Dependencies supplied to your set should be fakes in your test. A fake is a controllable replacement for a dependency. So by using a fake, you can test your code without dealing with the dependency directly. So instead of having to go to a real database, you can give your production class an implementation of the repository. As long as it implements that interface, you can tell it to do whatever you need it to do. So there are a couple of different kinds of fakes. One kind is stubs, and the other kind is called a mock. So a stub is just kind of a simple object that replaces a dependency, and it just makes happy noises basically. So if you call If you get a customer from the database, it will return some dummy customer and memory customer. So a stub is kind of just a dummy or anemic implementation of a dependency. It doesn't do much. It kind of lets your code or your test just run and test the code that you are concerned with. Mocks are for interaction testing. So a mock is more sophisticated than a stub. It'll keep track of method calls that are being made, and you can also, basically that's the difference, is that it tracks method calls that are being made, and it also tracks what those method calls are being called with. It'll track the data that is being called with those methods. Usually you use interaction testing if you have a third-party dependency that you don't have control over. So you're basically, in your production code, the result of that code is to call a third party. So in that case, you would use a mock just to make sure that a method gets called. So just to remind us, here are the two interfaces that we had in our previous example. And here are a couple of handwritten fakes. So on the left side, you'll see a stub date time, which implements that iDateTime interface that we saw earlier. In its constructor, it takes a time to return, and then when you call the UTC-now method, it returns that time that you told it to return. This basically, in your test, lets you tell your production code what time it is, or what time you want it to use. Then we have a mock customer repository, which is a little bit more sophisticated. It returns a dummy customer when you request the customer by ID. And then when you update a customer, it will keep track of the customer that you updated, the reference to that customer. So in your tests, you can basically, and here's our production class again, just to remind us. And here's an example of a test that uses those handwritten fakes that I just showed you. So like I said before, the three main phases of a unit test are the arrange, act, and assert phase, and I put those in comments in this test. So in the arrange phase, I set up everything needed for the test. And this test is basically just making sure that the customer gets registered when the customer registration class runs. So you take the current date, the date at the time that that line of code runs, and then you make a stub date time with that time. You create a mock customer repository. Then you just create a dummy customer ID, and then you create your SUT, and you do it with those fake implementations. So you create a new instance of that customer registration class, passing in those fake implementations. And so just to show you again the customer registration class, it takes those two interfaces in the constructor, and that's where we're passing in those fake implementations. So we create our production class with those fake implementations, and when it runs that register method, when it calls those dependencies are going to behave exactly like we configured them in the arrange phase of the test. So then we have our act phase, which is where we just call the register method, passing in that dummy customer ID. And we have our assert phase where we get the updated customer that was updated in our mock repository, and then we make sure that the registration date of that customer is the same date that we configured for our date-time dependency. Basically, we make sure that the registration date is what we configured in that fake date time, which makes sure that the registration date of the customer is set to the UTC now date of our date time dependency. So that's kind of a more sophisticated example of an automated test, and that's actually a pretty typical test. Just you set up your scenario and your data, you call a method in your test, the class that you're testing, and then you make an assertion making sure that the results are what you expected them to be. So now we'll talk about some testing frameworks that'll make writing testing easier. The examples I showed you before don't use any test frameworks. They were just kind of all handwritten. But after about a dozen tests or more, it's going to get really clunky to write some kind of a console app that instantiates all of your test classes and calls all of your test methods. So there are test frameworks that help you with defining unit tests. They also standardize how you make assertions to check that your results are correct, and they can help you create fake objects, etc. So some popular testing frameworks include MS-Test, NUnit, and XUnit. If you are thinking about starting automated unit testing kind of from the ground up, or just getting started with it, I would recommend XUnit. That's kind of become a more popular framework lately, and it's used by the .NET Core team. And .NET Core kind of supports it right out of the box. As a matter of fact, when you make a .NET Core test project, you can make an XUnit test project, but you can't make an NUnit test project. So I would kind of recommend XUnit.
Second, I always screw that up.
Right.
And
Yeah.
It thinks up on that for you.
Oh.
It tells you need to swap your parameters around.
Yeah, XUnit has more, I would say, the way it was written is more flexible than other frameworks, so it allows more extensibility, and that's why, I don't know, there's maybe some more features that have been written for it than something like NUnit. So these testing frameworks let you denote classes and methods for your unit tests, and they allow you to make assertions instead of throwing your own kind of exceptions. You can make an assertion that's kind of a standardized way of checking results. Your tests can be run, if you use these frameworks, you can run your tests in Visual Studio. Visual Studio doesn't support the non-Microsoft frameworks out of the box, but you can install adapters that will run tests from these frameworks. Also, if you have ReSharper, it makes it way easier. They have a really good test runner.
CodeRush does as well.
Yeah. So when you're using a test framework, your test classes and methods are decorated with attributes. And then whatever test runner you're using will find your tests by looking at these attributes. So you'll see in this example that I'm using NUnit, but you have a test fixture attribute to say that this is a unit test, and the test attribute to say that this is a test method. And you'll see the little green check marks next to them on the left, which is from ReSharper, basically saying it recognizes it as a unit test and that they've ran and that they passed. And here's an example test result from ReSharper. We had that customer registration test. This is just an example test result from running that test. So those test frameworks make it a lot easier to define your unit tests. Another kind of framework that you would want to use is a mocking framework. So in our previous examples, we used some handwritten mocks and stubs, but there are a lot of frameworks out there that will automate the process of writing those mocks. They will create a fake implementation of a dependency, and they'll allow you to modify the behavior of that dependency. So it includes some frameworks like MOQ, usually pronounced MockU, but it's kind of confusing, RhinoMox, TypeMock Isolator, etc. I've used the MockU framework in the past, but you just want to do some research on what fits your needs best. Here's a really simple example of using the MockU framework. You create a new mock of some interface implementation, and then you can set it up so that when a certain method is called with certain parameters, it will return a certain return value or do other things. Mocking frameworks also allow you to make sure that methods were called on your fake implementation with the expected data that you expect. So here's our customer registration class again, and the arrange phase of our test for that class with our handwritten fakes. And here's an example of the test rewritten with the MockU framework. You'll see that I create a couple of mocks and then I configure them. So when the UTC now method is called on the date time dependency, it will return the time that we want. And then when the get method is called on the repository, it will return a dummy customer. And then you'll see at the end that I make an assertion that verifies that our dummy customer was updated, basically that the update method was called on that mock implementation. Some other test frameworks you might want to consider. One is Fluent Assertions. It allows you to write assertions with a Fluent interface. You can see an example there on the bottom where you can make an assertion on what you would expect a string to be. One of the nice things with this is that if you switch from one testing framework like NUnit to another testing framework to something like XUnit, you don't have to learn the new assertions. Like if you learn the Fluent Assertion framework, it'll be consistent, you know. You won't have to. I recently switched to XUnit, and instead of learning that, I just started using Fluent Assertions, so I didn't have to learn the new API. So another test framework you might want to consider is AutoFixture. This is a library that automates the arrange phase of your test. What it can do is it can create object graphs with test data for you. So like if you need to create a dummy customer for a test, you could just tell AutoFixture to do it, and it'll go through the properties of that customer, and it'll fill it up with just anonymous dummy test data. Like all the string properties will be set to random GUIDs. Also, like it'll take care of the entire object graph, so if you have properties that are objects, it'll also create dummy objects for those too. It also will instantiate your SUT for you, so you don't have to call the constructor of your SUT, and it'll automatically supply mock dependencies if you want it to. So I have a couple examples here. I'm not going to go too in depth, but you'll see on the left our test as I wrote it without AutoFixture, and then on the right you'll see that I have an AutoMockData attribute and a bunch of parameters, which is where that framework just basically injects a whole bunch of dummy data and mocks that it will just create for you. So the arrange phase goes from maybe 20 lines down to 4 lines, but you have a lot more parameters in your test method. But it really simplifies things, so I would recommend it. So now another idea about maintainability is test naming and organization. So like your production classes, you want your test classes to have intention revealing informative names. Also, you want to keep tests organized, just like you do your production code, so it's quick and easy to find the tests for your production code. So each project in your solution should have an associated project with your project name .tests or something similar. You can have a test project for every production code project, or if you have a solution, you could have one test project for every production project in that solution. It just depends on how big your production projects are. So here's an example project organization. So you'll see on the left-hand side, let's see here. On the left-hand side, you've got a production.web project. And then at the bottom, you have a production.web.tests project. And it has, if you look at the right-hand side, I kind of expand the folder structure there. So you'll see that actually this is two different examples. One's with one test project per production project, and the other one is one test project for all of the projects in the solution. So for instance, you'll see on the right-hand side that there's a folder for the core production project and a folder for the web production project. So basically, you just want your test project structure, the folder structure, to exactly mirror your production code folder structure, so that you can say, where are the tests for the classes in this folder, or where are the tests for this production class? And you can just go to the exact same folder in your test project. So ideally, you should have one test class per production class. The problem is that, like production code, test classes should have a single responsibility or test one use case. So for test classes, that means that they should test one related set of behavior, or sometimes even one method. That keeps your test classes focused and manageable, but then you have the issue where you might have multiple test classes for every production class. So there are a couple of different options for organizing this. One is to make multiple test classes, each in their own file, and then make a folder for the tests of a production class named after the production class. And under that folder, you would just have all the tests for that production class. The other strategy you can use is just to have your tests in one test file, and have that file have multiple test classes inside of it. So here's an example of that. So on the left-hand side, you'll see an example of having a test folder for each production class when you have multiple test classes. And on the right-hand side, you'll see an example that has one test file for each production class, but on the bottom right, I go into the file, and you'll see there are multiple test fixtures in there, or multiple test classes. So test naming, it's important to name your tests well. Once a developer has located the test for a class, it should be easy for them to find the test for a specific behavior or unit of work. So the test name should tell a developer if the test fails, what was being tested, and under what circumstances. It should be very informative. So I include one convention here. You can have your unit of work name underscore scenario under test underscore expected behavior. That's one convention for test naming. So the unit of work is kind of the behavior that you're testing, and then the scenario under test is the circumstances that you're testing that scenario under, or that behavior under, and then the expected behavior is what you expect. So when this test fails, you're going to see, oh, just from the name, here's the behavior I was testing, here's the scenario I was testing for that, and this is what was expected, and it failed. You can choose whatever convention you want, but the important thing is to have one, and have one that makes sense. So now we're going to talk about integration testing. Unit testing is where you isolate classes from one another and you test them in isolation. And I showed you before by using dependency injection to isolate dependencies and things like that. An integration test is where you don't create fake dependencies for your tests. You actually use real production dependencies, and then you test them in concert, basically, to make sure that they are working together correctly. A lot of times with an integration test, you will hit a real database or a real web service. It's kind of outside of the scope of this presentation to go into integration testing. That's kind of its own topic, but that's basically the difference. An analogy that I've heard before is, let's say you have a vehicle, and you want to make sure that the car runs. Well, a way to test to see if the car runs would be to get in the car and drive it down the road. If it runs and it drives, then you know it works. But you might not be aware that one of the sensors is not working correctly just by driving it down the road. So driving a car down the road to see if it works is like an integration test. If you were to take the car apart and test every single part individually using specialized equipment for every part, that would be a unit test where you isolate every single part from every other part and you put it into some kind of framework that will test to make sure that it's running correctly. So that's kind of the difference between integration and unit tests. An integration test can be as small as injecting one real dependency into a class and then running a test, or you can test your entire application from end to end. So you could spin up a whole web service and make a call to that web service and make sure that it's getting you the right data or something like that. You can use a framework like SpecFlow for integration tests, and I'll let you look into that if you want to. So here's kind of a test pyramid of different kind of tests that you might write. At the top, that's supposed to be the least amount of tests that you have in your organization. And as you get towards the bottom, you should have more of those tests. And so you can see that at the bottom of the pyramid is unit tests. That is the type of tests that you want to have the most tests for. Above that is integration tests. Then end-to-end testing, which might be done through a UI. But of course, there's also MVC patterns that you can use to kind of isolate yourself from the UI. And then at the top is manual tests. Ideally, manual tests, you have the least amount of those. So the test pyramid kind of shows you ideally the amount of tests that you should have, the types of tests you should have relative to one another. So now we'll briefly talk about test-driven development. So once you become skilled enough with writing automated unit tests, you might want to start thinking about trying test-driven development out. So you can think about what is the ideal time to write an automated test. Is it after you write the production code, or is it before? So if you write your unit tests after you write the production code, and I've seen it to where writing your unit test could be as long as a month after the production code was actually written, or maybe even longer. You might not be familiar with exactly how that production code was supposed to work. The person who wrote that code at the time knew exactly how it was supposed to work, or you hope so. But if you write an automated unit test a month down the road, a week down the road, you don't really remember what that production code does exactly, and you might lose the spirit of what that code was supposed to do. You might also discover, if you write the unit tests after the production code is written, that a part or a large portion of the production code was written in a way that is not testable. And it may be impossible to write automated unit tests for that code unless you do large refactorings. So at this point, the chances of creating high quality, a suite of high quality tests is lower, because it's going to be more work. You're going to have to refactor your code to be testable so that you can isolate the dependencies, like in the examples that I showed earlier. So when you're looking at writing automated tests, if a large amount of refactoring is required for you to be able to do that, the chances of creating high quality tests it's lower. So when you consider those things, it's pretty clear that writing unit tests after the production code has been written will take more time. It'll be more costly than writing the tests at the same time as the production code. So when are you most familiar with how production code works? It's when you're writing it, right? So for that reason and a lot of other reasons, many developers have advocated that automated tests should be written before the system that you're testing, and this is known as test-driven development. TDD advocates say that if unit tests are going to be written at all, they should be written before the production code. Like there are different kinds of automated tests, there are also different kinds of TDD. There's TDD at the unit test level, at the end-to-end level, and also at the end-to-end level. So you'll see things like acceptance test-driven development, behavior-driven development, and other techniques. Like I've said before, it's important to start simple and then move to more advanced topics like behavior-driven development later if you want to. So the mantra of TDD is red-green refactor. This means you write an automated test for a unit of work under certain conditions, then you run the test and you watch it fail, you read the error message that's produced, and you make sure that the test failed for the right reason and that you can understand what the cause of the failure was. So you check the error message of the failing test and you say, can I understand what went wrong? Because 6 months from now, you might be reading that same error message. So you want it to be clear what went wrong. Then you write the production code in the SUT that makes the particular test pass. Only write the minimum amount of code to make that one test pass. So at times, this may mean that you might write incomplete implementations of production code, but it's an iterative process. So you write a test that checks a certain condition, you write the production code to make that condition pass, and then you move on to the next test and you iteratively move forward. So it's important that you write the production code right after you make the test fail so that you remember exactly what the spirit of the test means. So usually you'll write the production code that makes the test pass, and you do it really quickly, and you don't worry too much about writing clean code. Then you make the test pass, and then you go and refactor your code and make it clean and production quality, and then you rerun your test to make sure that it passes again. So that's what the red-green refactor steps mean. Yeah.
One thing, because I did a lot of research on this because my civil engineering had me do this.
Mm-hmm.
It is a huge leap. Two things that would make this a lot clearer. At the beginning, when you write your first test, compilation is an error.
Mm-hmm.
So when you write your first test, say, I need a class. Well, you don't have a class, that's a fail. So create a class. That's all you do is create a class. You come back like that.
Mm-hmm.
And at the bottom, you refactoring both the production code and your test, because your test will change as you do this.
Sure. Yeah, I agree. The compilation failures are failures. So
Most of the books I read didn't put that in. It wasn't until I watched the Uncle Bob video on this
mm-hmm.
that he made that abundantly clear, which actually made it correct for me, is that you can write a test that fails without knowing what's going to be next.
Mm-hmm. Yeah. So for example, you might have a class that implements an interface, and you could write a test to make sure that it implements the interface, but it's just a compilation error, so it's not always necessary. So it's a big topic, and it could deserve its own presentation or multiple presentations. So here's a picture of the TDD development cycle. You write a failing test, you make the diagnostics clear. That means check the error and see if it's understandable, then make the test pass, then refactor. So as you can see, it's a cycle. So that is pretty much what I had as far as content goes. So I have some recommended resources here. If you want to learn about solid and clean code, you can read Clean Code by Robert Martin. There's a great dependency injection book by Mark Seaman that you can look up if you want to learn that stuff. And for unit testing, I've read the Art of Unit Testing by Roy Osherov, and then there's another book called X-Unit Test Patterns. That thing is like the unit test Bible. It's huge. So if you guys want to dig into more resources, there are some good ones. So at this point, does anyone have any questions? We're going to go through some code briefly, but
What are some of the techniques that you need to have your tests run faster?
some techniques to make your code run faster. So
Tests faster.
Yeah. So one thing is that's important is when you're writing a unit test, like I said, that it's isolated from external dependencies. So one thing that makes a unit test run slow is if it's hitting a real database or a real file system or an outside resource that takes a long time to access. So when you're writing an automated test, it needs to be isolated from those external dependencies so that they're basically running in memory, and you're not accessing outside resources. So if your test is completely running in memory, it's going to be pretty fast. And what I've seen to make a unit test take longer to run is the amount of test frameworks that you use. So if you start using mocking frameworks, and then if you're using things like AutoFixture or other frameworks, they're doing a whole ton of work behind the scenes for you, which can make it faster to write unit tests, and it can make your unit tests more maintainable, but at the same time, it can make them slower. So you kind of need to look at, what is your test going through, or what is it doing, what data is being created, and you might make some adjustments depending on what you find. So, yeah.
You've got 1,000 times difference in speed between the frameworks. So you got to take your frameworks carefully.
Mm-hmm. Yep.
It's actually one of the first groups that I attended here was like the rapid fire one 2 years ago. One of the guys there actually had a benchmark of all the ones that he had to sell them. He would sell the right one to the boss with one of the interviews. And it was, so I think it's still up
Any other questions? So I'm not going to go into this. I have a code example here that I'm not really going to go into too in depth. But the slides for this presentation will get posted, within maybe sometime this week or next week. And my last slide here has a link to kind of an example of a project with some automated unit tests. It goes out to a GitHub repo. And I'll let you if you guys are interested in looking at it, it's an implementation of like a greed rules game, which is something that it's programming exercise that a lot of people have done before. So basically you write a console app that rolls the dice, scores it depending on certain rules. And I have the requirements of, the program there on the GitHub repo. And when I put the project together, I wrote some unit tests, and I did some test-driven development. And when I did that, it led me to, notice that first of all, I have to be able to fake my dice roll for my test. So you'll see one thing that I created a dice roll interface, which basically allows in your tests to make a fake dice roll for unit tests. And then I have an implementation of that, which is a random dice roll, and that's the production implementation. So you'll see a lot of tests where I'll create a random dice roll, and then I'll run it through a rule to assert that the score is correct. So if you guys want to check it out on your own time, it'll be there for you to kind of look through. But yeah, so that'll just give you an example of a larger, not large, but a larger project with unit tests. So. And that was pretty much all that I had. Yeah, so there's a link on the last slide to a GitHub repository that has the code.
I have one more question.
Mhm.
So often it is like and sprints, and it's like we have to deliver the feature as well as the tests with it. And often we don't get enough time to write as much as tests we would like, right?
Mhm.
So what is that, what's that idea to find the right balance between, or the right amount of coverage that you should have for the test? I mean, that would satisfy the business as well as you when you're satisfied with the coverage to the code.
Yeah, so I'll just throw a couple ideas out there, and these are just my opinions, but sometimes people go for a certain number of, a certain percentage of code coverage as a benchmark. So they'll say, we want 90% test coverage or whatever, and they can run a tool that will analyze your code and see what percentage of production code is covered by automated tests. And I realize the value of that, but I also think that it's not necessarily a good standard to have, because first of all, you can write a test that doesn't do anything, and then it'll count as code coverage. You could write a test that doesn't actually test what it says it's testing, or it might be faulty in some other way. So code coverage is not what I would say a great benchmark to say for your team, hey, we need to hit 90% code coverage, because under deadlines and things like that, a developer can go in and write something that looks like a test, and it'll bump the code coverage number up, but it won't really be a good test. So I'll make that comment. Second of all, when I first started doing test-driven development, I used to test every single thing. Like every line of code, production code had to have a test first. So I've had mixed results with that, and then over time, I kind of eventually settled more on an idea that is kind of been thrown out there, but by I don't know if it was Steve Smith who came up with it, or I'm sure it was someone else, but it's called pain-driven development. So pain-driven development is where you only use techniques and principles when you're writing production code and you start to feel the pain that those principles and techniques are supposed to address. So I really will only do test-driven development when I'm writing code and I get to something complex enough to where it's like, okay, I think I need a test for this. Like for example, today I was writing some code that parsed a file that was like delimited with colons or whatever. And I didn't write a bunch of tests for everything, but what I did write tests for was parsing each line of the file to basically say, here's a line of the file, here's what I expect the parsed result to be, and then I wrote a test around that, and then I wrote the production code that basically would parse it in that way. And I wrote multiple tests that checked different scenarios and things like that. So that's kind of my opinion right now. It could change later, but kind of when you start to feel the pain of code being complex to where you might not understand it completely at first, that's when you start thinking, okay, this is complex enough to write a test. But it's a highly debated topic, so you'll see a lot of opinions out there. So, yeah. Yep. Anything else? Cool. All right. Well, thank you guys.